It's the world's largest shake table facility, and it can hold buildings weighing up to 2.5 million pounds. The table moves in all 3 directions simultaneously. It's the first wood building of this size that's ever been tested.
The entire project is called the Niecewood Capstone Test, a project funded by the National Science Foundation. The project is led by Colorado State University, and Simpson was a close technical collaborator. The popularity of mid-rise wood frame construction has soared in urban areas, and so there's not a lot of information on how to design those types of structures. So the information gathered from this testing is going to be absolutely critical. The condominium tower was built as a actual condominium would be constructed with 23 1- and 2-bedroom living units.
We're testing a 7-story, 23,000 square foot, 800,000 pound building in 3 dimensions. This collaboration with all the folks involved is really going to culminate in a test that's going to show how our products perform in a very severe seismic event.
The forces of an earthquake on a structure of this size create a lot of secondary forces inside of the building, and the only way to hold those forces together is with connectors such as the ones that Simpson Strong Tie makes and provides. In this building, we have a wide variety of Simpson Strong Tie products, from large hold-down rods that run 7 stories up to the roof, known as ATS, or anchor tie-down system. We have a number of shear transfer elements in here, and straps and the floor plates to help tie the floor plates to the shear walls. In short, we're building what we call a complete load path.
This building, the Niecewood Capstone building, is designed using a performance-based seismic design philosophy. It's a method to design specifically for, or explicitly maybe, for performance of the building. We don't just design a component or an assembly. We actually design it all together and then we check it.
And performance-based design allows us, if we know enough about how the building reacts, to actually select what level of damage we want to see in the building during an earthquake. We're doing a series of tests on this structure so that we can incrementally increase our knowledge as to how the building is responding at different levels of shaking.
We're not only going back and forth, side to side, but we're going up and down as well. So we're getting all of the vertical accelerations and lateral accelerations exactly like that Northridge earthquake, but times 1.8.
There's approximately 300 sensors in the building, measuring everything from movement to force to acceleration.
Once that data and information is gathered, then it can be used to develop new design procedures and new construction methods.
So we're able to take what the engineers have modeled, compare it to how the building actually performed, and that's going to give us a lot of great data for years and years to come.
What we're really doing here is we're demonstrating that you can build a 6-story or even a 7-story possibly wood structure in a high seismic zone and have it perform how you want. It's safe, it's cost effective, and frankly they're very little damage.
Really, for 5% or less in your construction material costs in the beginning of the building, you can not only save the occupants of the building, but you can also save the structure.
This test will change the way light frame wood is designed over the next 10 years.
We've invited several key engineers from across the country, building departments. There's folks from all over the world coming to see this.
When you see an actual test, the impact that has on you is so significant that it really makes you think twice about what you put down on paper.
Everything in it worked. There was minimal damage to the inside of the building, minimal damage to the outside of the building.
I would say that this testing really does validate the performance-based design concepts developed at the various universities involved in this project.
It's phenomenal that we can have a test of this size and magnitude of a building like this and actually get some real test data.
Simpson never forgets, and they're always trying to make sure that they're really providing what the structural engineering and construction community needs. And I've always been impressed with taking that extra step to really know the science part of what we do.
It's truly unprecedented what they've done today. I think this is it's truly about saving lives, and the information that's been generated as a result of this test is truly groundbreaking.